Hello everyone. In the today's Ansys tutorial, we are discussing stress analysis of varying cross section or stepped bar, and also uh, different material in each step. You can see that the Young's modulus is different in this step, and Young's modulus is different in this step. That means this is two different materials combined together with the varying cross section. So the problem description is to perform the displacement and stress analysis for the given stepped bar using Ansys simulation and analytical expression. So given we have Young's modulus and area is 900 millimeter square for this step, and the area is 600 millimeter for this step, and a load of 500 Newton is acting at the free end. One end is fixed, that means at node 1 we have zero movement. Displacement at node 1 we have zero movement. We have displacement in this portion and this portion. The maximum displacement will be here. So let's move to the theoretical solution. The length of the step is 600 millimeter and 500 millimeter. Total length is 1100 millimeter. So given Young's modulus for element 1, this one is 2 into 10 raised 5 Newton per millimeter square, and Young's modulus for this one is 0.7 into 10 raised 5. That means this is approximately a steel material, and this may be aluminum or another light material. So deformation, since it is fixed at one end at node 1, we are assuming this as node 1. At node 1 the deformation will be 0 since it is fixed. At node 2, that means this portion we have to calculate by using the formula PL over AE. So substitute that P, we know that positive 500 and the length is 600 millimeter, you can see, divided by area 1 is 900 millimeter, which is given, into Young's modulus is 2 into 10 raised 5. We'll get, if you substitute all this value, you'll get the deformation at node 2 is 1.667 into 10 raised minus 3. This portion we have a deformation of the approximately 0.00166 millimeter, and at node 3 this portion we have you have to calculate the displacement. For that you have to add this one, this deformation plus deformation in this portion. So we are keeping these same values here, you can see, and addition of deformation in this portion. So P is 500 and L2 is this portion is 500, and area is 600 for this portion, and the Young's modulus is 0.7 into 10 raised 5. So if you substitute all this, we'll get a value of 7.619 into 10 raised minus 3 millimeter. So this is the maximum deformation at free end. So next, the stress, we have two elements here. So the stress at element 1, since the area changes, we have two different stress for two elements. So load is constant, that is 500 divided by area 1 is 900, will get 0.5556 Newton per millimeter stress at this portion, and the stress 2 is load by area is changes here 600 millimeter. So if you substitute that, we'll get 0.833 Newton per millimeter square. And the reaction, so R1 plus R3 equals to 0. We know that R3, that is load at node 3, is 500 Newton. If you substitute it here, R1 plus 500 will become 0. So R1 will become minus 500, and R3 we know that it is 500 Newton, which is given. So the theoretical calculations are over here. Let's move to the Ansys software, and we have to solve everything in the Ansys, and you have to compare this answer. Let's move to the Ansys. Click here preferences, go to structural, click on OK. Next, preprocessor, element type, add, edit, delete. Add, go to link 3D finite STN 180, click on OK, click close this, then go to real constant, add, edit, delete, click on add, click on OK, click the area as first area is 900, click on OK. Now you have to add the another set, because we have two different areas, so you have to add here. Select the link 180, OK. You got real set constant set number 2, that is area 2 is 600, you have to enter here. Click on OK. So we got two sets here. One is 900 millimeter, another one is 600 millimeter. So close this. Then go to material properties, material models. Click on structural, linear, elastic, isotropic. Remember that we have two different materials here. So first element we are having a Young's modulus of 2 into 10 raised 5. So 2e5 I will write here. And the Poisson's ratio is not given. We are assuming is at 0.3. Click on OK. Now for entering the properties of second material, you have to go for material new model. This is very important. The people will do mistakes here. They will not add second part here. So you have to go for material new model. So material ID number 2 will come here. Click on OK. You see here again, for this you have to click on structural, linear, elastic and isotropic. And here you have to write the Young's modulus of second component, that is 0.7 e raised 5. And again we are assuming Poisson's ratio as 0.3. Click on OK. Now we got two different metal number 1 which is steel, and metal number 2 which may be aluminum or another light material. Click on close this. Then go to modeling, create, go to key points, in active CS, click the right here 1, click on apply. The first key point is created at origin. If you don't give anything, automatically it will take as 0. So second part, you have to write second key point and you have to give the distance as this is first distance is 600 millimeter. Click on apply here. Now give the third key points. Combining distance is 1100 millimeter. Click on OK. So 3 key points are created in the screen. So using these 3 key points, you have to create a line. Go to line here, create line, straight line. Click on 1 to 2. Click on OK. Again go to straight line. Click on second to third key point. Click OK. Two different colored lines will be generated here. Then you go to meshing. Once modeling is over, you have to go for meshing. Then go to mesh attributes. Here go to picked lines. Then select the first line. Click on OK. Now for this set here, very important. You have to change the properties. Everything is in this meshing part only. So this first line is related to real constant number 1. We have two materials here. Then you have to select the real constant number 1. Here also you have to confirm that we are in real constant set number 1. And this remains constant for both material. Click on OK or apply. Again click on second line here. Click OK. Now you have to change the metal number to 2 because we are the area of the metal number 2 is different, metal number 1 is different. So this second line, what is there here, this is your second part. Here area is changes, that is 600 millimeter. Length also changes and also the material properties also changes. So you have to make this metal number as 2. In the earlier problems we have same material throughout the same material. So this we have not option 1 and 2, only we had option of 1 because we have not changed the created new models in the earlier problems, which is having same these things materials throughout the length. So but here in this problem the material changes from one step to second step. So I have to change the second step here, and this also you have to change here. The material properties will change like Young's modulus. Here the area will change. So every for second line you have to keep this as second, and real constant set number also second. This remains same for both the cross section. Click on OK. So different materials and different areas is applied to these two lines. Now go to mesh tool, mesh tool, you go to size control, click on manual size, global size, click on 100. This you have to give 10, and this division should be 100. Click on OK. Now go to mesh tool, click on mesh, select the pick all here. Now meshing is done. Then go to solution here, define load, apply structural displacement on key points. You have to fix this key point because this is fixed. You have to arrest all the degrees of freedom. Click on this key point, click on OK. Now all DO you have to select, click on OK. You can see this is fixed. Now go to applying a force moment load, apply force moment on key points, select the third key point, click on OK. Now FX direction, you have to give positive load of 500 Newton, click on 500 Newton, click on OK. Now the load, everything is applied, you can see here. Now go to solve current LS, click on OK. Solution is done, close this, and go to general post processor, click on element table data, not this one. So you have two element table data, so you should not confuse here. This is not in the list result. Go to direct here. We have element table, that define table, add, go to by sequence number, click on ls, comma 1, click on OK, close this. Now go to, everything is over now, you have to go for seeing the results. Then go to plot result first here for plotting the results. Then go to nodal solution, deformed shape, deform plus undeformed, click on OK. You can see the maximum displacement 0.007619, which is exactly same as the theoretical calculation. Again go to element table, click on OK. You can see the stress here, that is 0.55 and 0.83. This portion we have 0.55 and this portion we have 0.833. Then you go to line element result, click on OK. You can see by graph, this is this stress is less here in this element 1 and stress is more in this element, that is 0.55 and 0.833, which is exactly same as the theoretical calculation. Then go for least result, go to reaction load, reaction solution. This will shows you the reaction forces, that is 500 at node 1, which is same as the manual calculation. Then go to element table data, click on ls1. See here the stress, since we have divided the elements into number of divisions, so in each element it will give the nodes. The maximum will be 0.5556 and 0.883, which is same as our calculation. Then go to nodal solution, X in DUF solution, X displacement vector sum, click on OK. Here you will get the displacement. You can see the maximum displacement is 0.762, which is same as the manual calculation. So everything we got the result as theoretical solution. So that's it for the today's session. Thank you.